Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
My name is Hector Levesque, and I'm a professor emeritus at the University of Toronto, which is just a highfalutin way of saying that I'm a retired professor from the University of Toronto.
Well, congratulations on your retirement.
Thank you.
During your more, formal time there, tell me a little bit about the research you were interested in.
Well, I've been in the area of artificial intelligence since I started working there about, 30 years ago or so, in one particular area of artificial intelligence called knowledge representation and reasoning. And I've pretty well stuck to that area my whole career, looking at a variety of problems in that area. So that's knowledge representation and reasoning within artificial intelligence, within computer science, within arts and science at the University of Toronto.
Got it. During your tenure in the field, how much has that changed?
Well, it's changed pretty radically. It has its ups and downs, and the ups and downs in artificial intelligence tend to be wider in some sense than other areas of computer science. People get more excited about the successes and hype them more and get on TV more and make the New York Times and so on and so on more than other areas of computer science. And similarly, when areas fall into disfavor, there's more attention to that as well. And so there's been ups and downs and swings of various sorts. The area of artificial intelligence that I was involved with, knowledge representation and reasoning, had a very large upward push, if you'd like, a boom for a while. And then people sort of got a little worried that it wasn't leading to the kinds of applications and products and services they wanted in a nice and easy way. And so money moved elsewhere. And about 10 years ago, money moved very drastically towards the area of machine learning, and for good reason, I think. And so almost all of the attention in artificial intelligence today is very different than what it was 20 years ago. Namely, it's concerned with machine learning and learning from big data and things of that nature. That wasn't around 20 years ago at all. It was much more the kind of AI that I've been involved with, reasoning, logic, probability to a certain extent, and so on and so forth. And so that is a big change.
And do you think that'll spill over? Will we, have some sort of deep learning first-order logic coming about at some point, or are these distinct methodologies?
Well, they are very distinct methodologies, and it's hard to see where they touch. And I think what we are going to see, like all the other past waves in artificial intelligence, is that it will move on to other things. I don't think artificial intelligence will stay with very narrowly construed machine learning for a long period of time as it is now, because people are going to start realizing some of the limitations of looking at AI from a very narrow point of view, and it'll move on to other things. It's hard to predict at this stage what those other things will be, but there have been, as I say, previous waves where people for a long time thought, for example, that automated theorem proving was going to solve all of the problems. And then it was expert systems were going to solve all of the problems. And then it was situated robotics is going to solve all of the problems. And then it was automated machine learning. And there have been various other little waves in there as well. In a talk I gave once, I called this serial silver bulletism. And what I meant by that was that a tendency to think of silver bullets for AI, but in a very serial way. And you take one silver bullet on, and then you sort of say to yourself, all the previous silver bullets were a waste of time. But now we've really got the story settled, and this is the silver bullet that's going to kill AI. And then 10 years later, we sort of say, oh, that was crazy. We really know that now it has to be done this way, and so on. And AI, unfortunately, has had those kinds of swings over its history.
Yeah, very true. When I was in grad school, we were discussing this thing called the AI winter that I guess at that point people were saying, oh, we're past it now. Do you think we'll continue to see swings of that nature, or is there going to be an AI dark ages or anything?
No, I don't know if there'll be an AI dark ages, but what's going to happen is that the money will shift again as it's been doing in the past. And I think the winter really has a lot to do with the money. The ideas keep on coming, but the ideas are much more constrained. There's smaller groups of people involved with it in universities typically and whatnot. It's very research oriented, but it's the applications, the technology that gets all the attention. And I think the technology will move and swing, and there'll be summers and winters in AI in the future, just as there's been in the past.
So as this interview airs, people will have just heard our episode on the Turing Test. Can you give me your perspective on the effectiveness of that test, or maybe its usefulness?
Well, it was a thought experiment that Turing had, in my opinion. And, I think the actual details of what he wanted and what he didn't want are less important than what he was getting at. And I think what he was getting at was that when it comes to discussing these hard concepts applied to people, such as the idea of being intelligent or thinking, or even being conscious, that it was going to be possible for people, reasonable people, to disagree about what those things meant and to disagree whether or not a machine would be exhibiting them, whether a machine was thinking or was being intelligent or even being conscious. And he, I think, wanted to push the conversation in a very different direction and wanted people to focus instead on a question more like, well, we should be looking at the external behavior of machines and people and asking whether it's possible to get a machine not so much to think or to be intelligent or be conscious, but to act like it is intelligent or thinking or conscious. So focus on external behavior. And I think that's the push that he was aiming for. And then he ended up trying to say, well, what kind of external behavior, externally observable behavior would make sense to look at when we're thinking about general intelligence, the kind of intelligence that people exhibit. And he came up with this idea of having a conversation, and that's the imitation game, as described, I'm sure, in your previous podcast, where the idea is that there's an interrogator talking over a distance, say over a teletype, to both a person and a computer. And the issue is whether over a period of time the interrogator can tell the difference, which is the person and which is the computer. The conversation is supposed to be completely unconstrained about anything, natural, just a regular old conversation. He said that if a computer over a long period of time, if the interrogator couldn't tell which of the two participants was the person and which was the computer, well, then the computer had passed this test, which we now call the Turing Test. So to pass that test is being able to converse well enough with an interrogator that the interrogator can't tell who the person is and who the computer is.
But over the years, there's been some questions about whether or not it's the most effective test. And I think the leading, at least to my research, the leading idea that maybe could surpass that or extend it is this concept of the Winograd Schema challenge.
Right.
And that's how we ended up getting in touch. We read your excellent paper titled The Winograd Schema Challenge, which will be in the show notes. For those who aren't familiar with it, can you give a definition of what that is?
It seemed that the Turing test focused too much on whether or not a participant computer program could fool an interrogator, was concentrating on deception, whether or not you could pretend to be intelligent and what it would take to pretend to be intelligent in a conversation. And that it encouraged people to look at chatbots that were very good at deceiving interrogators by various means, by being evasive, by having points of order, by changing the subject when it was awkward, and so on and so forth. In other words, without being intelligent or anything, just finding ways to fool interrogators using conversation to do so. And so I wanted to think about what it would be like to have a test that was behavioral the way Turing wanted to, but didn't have the kind of flexibility that an ordinary conversation would, so that it would be harder for subjects to game the test by doing evasive behavior and maneuvering of various sorts. The first thing that occurred to me is, well, why not have questions for the computer program that it has to answer and make them multiple choice questions, so it doesn't even have to speak in English at all. It'll just choose the answer from a bunch of questions. And I think if those questions aren't formulated properly, there are tricks that you can do to do pretty well answering the questions, again, without being very smart, without knowing very much, but just by, if you like, gaming the questions, looking at the questions for certain patterns and so on and so forth. Although I think I was on the right track there, I wasn't happy with the sort of general question answering framework. And so I thought of a very narrow type of question that you might pose to a program to see if it was understanding what you were talking about. There was only going to be two answers to the question. If you changed one word in the question, the answer could go one way or another. So you wouldn't be able to guess very well or use cheap tricks to answer the questions. And so we constructed Winograd schemas. If you like, I can tell you how these schemas are formed, but that's the general idea. So it's a question that you would ask a program, and the program has to give you the right answer and the questions are constructed so that it's tricky to guess at what the answer is in a very deliberate way. So they're not naturally occurring questions that you would find in a book or something like that. They have to be made up by researchers, but there are questions that people can answer easily, but that are tricky to answer by cheap tricks, if you like, without understanding what's going on. So here's the first example I had in a paper I had. You give a sentence, and then you ask a question about the sentence. And the sentence is this: the trophy wouldn't fit in the suitcase because it was too small. What was too small? Was it the trophy or was it the suitcase? Two things are mentioned: a trophy and a suitcase. It says that the trophy doesn't fit in the suitcase because it was too small. You don't even notice, you don't even hear the it when I first say the sentence or when you first read it, but I want you to focus on the it. So the trophy wouldn't fit in the suitcase because it was too small. And the question is, what's the it? To understand that sentence, to be able to answer the question about what was too small, you need to know what that it is. And the it could be the trophy or it could be the suitcase. And the job is to figure out which one it is. Now, people, when you hear that sentence, if you speak English at all, then you have no trouble answering that sentence. And you figure if I say the trophy wouldn't fit in the suitcase because it was too small, it's the suitcase that's too small, not the trophy. But the interesting thing is if I change one word in that sentence and I say the trophy wouldn't fit in the suitcase because it was too big, then you have to rethink it. You have to sort of say, oh, well, in that case, because it's the word big, the it in this case has to be the trophy that was too big. That's the idea. You've got a sentence, you've got a pronoun in it. In this case, the pronoun is it. You've got to figure out what that pronoun is between two things, a trophy or a suitcase, and people are able to do that very easily, but it's tough to do it with a special trick. You have to understand that if something doesn't fit in something else, it's because one of them is small and one of them is too big, and you got to know which one is which, and that's how you answer the question. That's one example of a Winograd schema, and there are a bunch of them that have been collected in the library that all have that same property. There's two things being referred to. There's a pronoun, and you got to figure out which word the pronoun, which noun the pronoun goes with, and the way that you figure it out is you use what you know about the world. It's not difficult for people to do, but it is tricky to do because you can't look up these sentences on the internet. You can't Google them. You can't look them up in books and whatnot. They're brand new sentences. And so you really have to understand what's going on. So that's the proposal, roughly speaking, for the test. You give a bunch of those to a computer and you see how well it does compared to how well people will do.
So a previous guest I interviewed about question and answering software pointed out that in their case, they were asking multiple choice questions where there were 4 answers. So obviously random chance is 25%. And using some very, very simple information retrieval techniques, basically mutual information, they were able to get half those questions right. Which is not astounding, but in a way it is. That's just these very brute, naive techniques get you pretty far.
Absolutely.
And I assume that we'd get a worse score, probably closer to 25%, if that same approach was applied to Winograd schema questions.
Right. So that's right. You certainly have the option of guessing, and there are some syntactic things you can do, so some small tricks that might get you slightly better than random, but at the state of the art right now is not a whole lot better than random. And yet, these questions aren't hard questions. They're not questions that people would have a tough time with. People would very easily get almost all of these kinds of trophy suitcase questions very easily. Let me just give you another one just to reinforce that point. Jane made sure to thank Sue for all the help she had given. Who is it that gave the help? Was it Jane or was it Sue? Again, it's exactly the same type of sentence. There's the word she appears in there, the pronoun she, and you've got to figure out that if somebody thanks somebody else, who is it that gave the help and who is it that received the help? If I change the word to received, so if I say Jane made sure to thank Sue for all the help she received, well, then you interpret it completely different. Okay, so it's Jane that received the help, it's Sue that gave the help, and that sort of kind of thing. It's tough to find little statistical tricks you can do to help you do much better than random. But again, these are not the kinds of sentences that people would sort of look at and shake their head and say, no, this is impossible. I have no idea what the answer is. They're just ordinary sentences. They're new. They don't show up anywhere else. You can't look them up or anything, but it doesn't require rocket science to answer them either. You expect that any, as I say, normally abled English-speaking adult wouldn't have much trouble with them. So the difference there is that people get almost all of them right, and a computer program without an understanding of what the words mean and the ability to put these words together and use what they knew before they heard the sentence wouldn't do much better than random.
Yeah, so to go to your example, Joan made sure to thank Susan for all the help she had given, who had given the help.
Correct.
Like you said, it's such an automatic thing. I just know the answer somehow. I'm not
Yep.
even sure. I'm not consciously running an algorithm to do it. And in some way, I'm confident I'm relying on a lot of the knowledge representation my brain has. I know something about help and that one should issue a thank you for it.
Right.
That's even maybe cultural.
Yeah.
That seems to be the connection that's tricky. Am I looking at it the right way?
No, you are looking at it exactly the right way. And it very definitely is cultural. You can easily construct these kinds of sentences for which people that are from a different culture would have a hard time answering them. You can also construct sentences that young children would have a hard time answering. Really, when I say that adults would get almost all of them correct, that's really a simplification. What you'd really need to do is take these sentences and check for the people subject you have in mind, whether or not they understand what the words that are in the sentence and how they're going to be used. I gave an example in a paper involving the word styrofoam. I said the ball crashed right through the table because it was made of styrofoam.
Aha.
If you don't know what styrofoam is, you're not going to be in a good position to answer whether it was the ball that was made of styrofoam or whether it was the table that was made of styrofoam. If you know what styrofoam is, well, then you figure out it's not the ball. If the ball crashed through the table, it's the table that was made out of styrofoam. But you need to know that. If you don't know what styrofoam is, you're not going to be able to do anything with it. So as I say, these sentences have to be selected and tested very carefully before you actually use them in a real test with people versus machines, if you like. But the point is, once you do know what styrofoam is, even though you've never heard the sentence I just said before, you are going to be able to sort it out that it was the table that was made of styrofoam. The alternate, if I said the ball crashed right through the table because it was made of solid steel, you'd give me a completely different answer, what the it was. The it in this case would be the ball that was made of solid steel, because you know what steel is, and you know that steel is very different from styrofoam and so on and so forth.
Someone who has a lot of confidence that just the very idea of big data is going to solve all the world's problems, they might look at this and say, well, we just need a bigger corpus. Eventually there'll be enough data and examples that some statistical technique or some collection of techniques will be applied in some ensembled method, and they'll be able to catch this.
Yeah. I think it's a plausible answer, but it's not one that I believe in. I just don't think that there's ever going to come a time where you will exhaust all the possible things that you can say in English, that all the sentences will already have been said, and you'll just be a matter of looking them up. That's just not the way English sentences work, and it's not the way putting together pieces of knowledge work. There are always new things. There's always unexpected things that you could say. I mean, if that were true, people wouldn't write new books, right? They'd sort of say, well, what's the point? Well, I think we've exhausted everything that could be said on page 1 by now, right? And that's just not what happens. And it's not what happens with what we meet in our ordinary day-to-day life as well. It's not that everything we see is now familiar. No, we're constantly getting new things for which we have no experience. So the point about these sentences is that they are brand new. You don't expect them to be already tested somewhere, and it's just a matter of finding them and finding out what the answer is somewhere else. So my feeling is, anyway, that this does go beyond big data, and that's what motivates, I think, a different approach to at least some part of AI, that there are these unanticipated things that are going to come up that you're going to need to deal with, and that you're not going to be able to rely on the training that you've had, even if it's over very, very big data, to deal with it. You're going to have to sort of step back and sort of say, well, this is something that's completely new, nothing I've seen like before. What do I do now? These sentences are just a special case of that. They're sentences that are brand new, but there are situations that are brand new that AI systems are going to have to deal with. And I think that's a concern when it comes to machine learning and big data as your only source of intelligence for dealing with them.
The Mendoza College of Business is a comprehensive business school at the University of Notre Dame. They offer a Master's of Science in Business Analytics degree that might be a good fit for you. It's a 12-month program in their Michigan Avenue, Chicago campus. Classes meet alternating Fridays and Saturdays, 9 to 6, and there are 3 3-day intensive sessions on Notre Dame's historic campus. Do you have a good grasp of quantitative topics, methods, and tools? But do you lack the experience and the know-how to apply them to business? Maybe the classroom interactions with award-winning faculty can help advance your career. See if this program is right for you by visiting mendoza.nd.edu/dataskeptic. Visit that link and your application fee will be waived. mendoza.nd.edu/dataskeptic. One thing that's kind of had a lot of influence on the way I think is looking at certain types of problems and seeing how a new innovation brought a solution for them. So we could think about how Markov chains were applied to sentences. And, if you look back one or two words, that work, for certain things that works pretty good.
Absolutely.
But people noticed very quickly that, there are times when, at the beginning of our conversation, you mentioned you were in Toronto and it's not come up since, but it's still in my short-term memory. So they've introduced ideas like the LSTM, the long short-term memory, where maybe a machine could learn to preserve that bit because it's going to be relevant contextual in some way.
Right.
Do you think it's just algorithmic techniques that we haven't been clever enough as humans yet, or is there something else missing here?
Well, that's a good question. I'm really not sure, but I agree completely with your point, which is to say that there, for the large majority of cases we're going to be dealing with, it will be simple and it will be based on things we've already seen. And there are going to be simple ideas like using test cases we've seen before and learning from big data that'll deal with a whole lot of the day-to-day phenomenon that we're dealing with. I think where we have to be careful is where that doesn't hold. In other words, if you're doing a Google search and you happen to type in the wrong things, well, nothing bad follows from it. You type in something else and away you go. If it doesn't quite understand what you're after, no one's going to die. It's not going to be a big deal. You just try something else, and sure enough, that works fine. And I think a lot of what we deal with in life, if we run into a problem, we just kind of shrug our shoulders and move on and try something else and see what works better. And we have algorithmic ideas for dealing with a lot of these very common kind of situations like that. Where we have to worry, I think, is where there are some rare situations that can make a big difference overall. And that's something I concentrate on in my book, is worrying about these rare situations that are nonetheless significant. So, if you're controlling a nuclear power plant and funny things start happening, you don't want a system that's running this nuclear power plant to just shrug its shoulders and try something else. You want it to step back and start saying, well, hang on, if I make a mistake here, it's going to be very, very significant, even if it is rare. So it's not good enough in a situation like that, if you're driving a plane or driving a car even, or controlling a nuclear power plant, that the vast majority of cases are handled by simple means. That's just not going to cut it. Not going to cut it. Why? Because those rare things that can happen can be very, very significant nonetheless. Even if there's only one chance in a million that it happens, if it can have a catastrophic event, result can come out of it, and it can mean the end of humanity, well, that's something we have to care about.
Absolutely. So since reading the paper, I was trying to just run through sort of a mental exercise of my own and kind of catalog what my knowledge base was in my own mind, even implicitly with some of these questions. Like, the trophy doesn't fit in the brown suitcase because it's too big. What's too big?
Yeah.
I know so much about that I take for granted. Like, for example, I'm aware that a large trophy is probably a desirable thing. And that, I presumably have, there's like a whole story here. I went somewhere to get it. That's why I have a suitcase.
Yep.
How do the current state-of-the-art knowledge representation systems compare to what's presumably somewhere in the wetware of my brain?
Yeah, that's a really good question. I mean, the KR people, the folks that do KR, we're in the minority these days in terms of artificial intelligence research. All of the attention has gone to, or at least a lot of the attention has gone towards machine learning. But there still are a number of people that are actively involved with this, but the progress has been slow. It's tricky to sort out what exactly you need to know to be able to answer these kinds of questions, or just to behave in a reasonable way when you're faced with unexpected, unanticipated situations. So what it is you need to know on the one hand, how do I represent that in a computer, and how do I get a computer to use it? There are ideas on all of these things, but they're all very, very tentative. I think it turned out to be a very, very difficult problem to sort out how all these things should work, how they should fit together. And I certainly don't think it's ready for prime time yet. I don't see in the near future technology that can solve these problems in a general way that does as well as what we see happening in people. As you pointed out, and you're quite right, when you read some of these sentences, you don't even notice that you're solving these problems and figuring out which of the two alternatives is what the pronoun is referring to. It happens so quickly in your head. So it is a process that we see happening in people extremely quickly, but to sort out what that process is, what it's based on, and try to understand it in terms of what you need to know and how you use what you know, that still is a largely, I would say, unanswered question.
Yeah, the fact that we do it quickly is something I've been hung up on in a way. Even image recognition, not that it's related, but these things where in just a moment, what seems to be big O of one constant time, my brain has sorted something out.
Yeah.
And obviously, I think we know on some level it's doing that because it's a massively parallel machine.
Yeah.
But it's also kind of perplexing to me because these are difficult problems with the tools I'm aware of algorithmically today. And those, I run my algorithms in polynomial time or worse.
Right.
Do you think there has to be some sort of fundamental shift where knowledge representation is getting into these constant time algorithms, whatever that even means?
Well, I don't know about constant time algorithms, but let's say at least logarithmic time algorithms. That is to say, you want to be able to deal with very, very quickly with, if you like, millions of facts. And the only thing that makes sense for that is that it be logarithmic and not linear. I think that's a more reasonable alternative that will give you the performance that you need without sort of expecting that it'd be constant time. To suggest that it's constant time almost suggests that there's only a fixed amount of information that it can deal with, and if you learn more, well, then you're sunk, and that doesn't seem to be the case. But what does seem to be the case in people anyway is that you can learn more, and overall your behavior improves. And yet all the algorithms that are polynomial and whatnot, it's just the opposite. Give it more facts, and it just got more stuff to work through, and it slows down and things get worse. And I think that's a big puzzle. That is to say, how is it that when we learn more stuff, our behavior actually improves and we don't get more bogged down? And I think the complexity of that must mean that we are dealing with things in at least a logarithmic way, so that it takes a lot for us to bog down because we get to the relevant parts of what we need to know very quickly. But constant time, order one time, seems a bit too much for me.
Right. Yeah, actually, I think you're onto something there. It would maybe be easy for me to overestimate that my brain is running some logarithmic time algorithm that I'm unaware of just because of its speed. I'm getting a seemingly instant answer, I guess.
Right. Yeah. Well, you can be seemingly instant if you're logarithmic, even for a very large number, right?
Yes.
If it only 20 steps to look at a million facts, then I think, that can seem like it's constant time. It can seem like it's instantaneous, but in fact, it can just be 20 steps for a million facts. I don't know a million things about Peru, for example. I only know 20 things about Peru. So you know what I mean? So you start adding up what you know about this and what you know about that, what you know about trophies and what you know about suitcases, what you know about the sizes of physical objects. Well, yes, the facts add up, but possibly not into the trillions, more like into the many thousands or maybe millions of facts.
You've mentioned a couple times assembling these questions. Is there a corpus that researchers can get access to maybe build their systems against?
Yeah, a co-worker of mine at New York University called Ernest Davis in the computer science department there has on his website a growing library of these sentences, so you can look at them and sort of see what they look like. They're not going to help you if you're going to try and do some sort of learning from them because they're all very, very different from each other. They all have the same structure, but the words are different and so on and so forth. But I'll give you an idea of what the range of sentences that people have been thinking about. And there is a competition that's being held, or that has been held at the AAAI conferences. There's already one that was held where people submitted programs to try and deal with these sentences. The programs themselves didn't get very far, but that competition is still ongoing, I believe. I'm not really involved with it that closely, but it's sponsored by Nuance Corporation in California. I think your listeners will be able to Google these and find them, or if not, I can send you links to them.
Yeah, absolutely. I'll put a few in the show notes because I think that's a really interesting conversation to watch. One of the most recent competitions, I don't remember the number, but I think the winner was something like 55% accurate, where 50% would be random chance.
That's right. And I think there are a number of these questions that do have patterns to them, a number of these Winograd schemas that have patterns to them. And if you're not careful, you can do a little bit of pattern matching there. But again, you're nowhere near the kind of achievement that untrained English-speaking adults would be able to do on them, which is to say getting almost all of them correct with no effort at all. And again, it's not as if adults need pencil and paper and a lot of time and, be in an exam room and have perfect quiet or whatnot. You don't even notice they're a problem until someone points out to you that, you know what you just did? You figured out that the it meant the trophy in that. Did you realize that? And they sort of go back and sort of say, yeah, I guess I did. There are problems that are easy, in a sense, for people to do, but again, quite difficult for programs to do much better than random on, at least at this stage.
Right. Yeah, when I look at some of these and I think, Well, what about it is tricky? Why would a program struggle with this particular one? And, in some other domain, it can answer elementary school science questions, but it can't answer these schema challenge questions.
Yeah.
I find that it always, the explanation I'm telling myself is that, it's that the algorithm doesn't know something. It's missing some simple fact that I have that I take for granted.
Yeah.
And that being true, it leads us quite naturally to saying that we need some sort of breakthrough in knowledge representation. Would you agree? And if you met an aspiring young grad student who wanted to pursue that, do you have any advice for where they'd go?
Yeah, I agree completely. That is to say that it seems that the reason why people do these so easily is that they know stuff before they even see the question. They know stuff about styrofoam. They know stuff about the sizes of things and so on. So it is a knowledge representation problem. It's not a language problem per se. It's the problem of knowing stuff and being able to apply what you know to the task at hand. And the task at hand in this case is just being able to answer these questions. So I agree completely. It's a knowledge representation problem. I wouldn't encourage graduate students so much to try and solve this problem specifically, because I think that tends to focus you on looking for tricks, looking for ways of somehow doing slightly better than random and so on and so forth. What I would encourage grad students to do is to step back from the task itself and sort of say, okay, we accept the fact that you need to know a lot and you have to be able to apply what you know to be able to answer these questions. What kinds of knowledge do you need to know? How would I represent that kind of knowledge? What kinds of algorithms would I need to apply to those representations to give me the conclusions I would need to be able to answer these kinds of questions? So step back from the test itself, if you like, and sort of ask, what are the prerequisites to being able to do well on this test, and focus on those.
So your book is titled Common Sense, the Turing Test, and the Quest for Real AI.
Right.
Can you tell listeners a little bit about what's inside?
It's my attempt to sort of describe the part of AI that doesn't deal with machine learning, the part of AI that deals with thinking and reasoning and knowledge representation and so on, from a non-technical point of view, trying to motivate why you would want to do more than machine learning, and explain a little bit what the fundamental ideas are behind the other part of AI, which was basically all of AI up until about, 25 years ago or so, and what it hopes to achieve and how it goes about doing it. The emphasis is on this idea of common sense, the idea that there's a certain body of common knowledge that a lot of people have, that you're applying that when you're faced with situations that aren't like those you've seen before, and that's what allows you to behave in reasonable ways when you get these unanticipated situations. And it can't be achieved by training because there's too many of these unanticipated situations. They're very rare anyway. They don't come up necessarily often. And sort of explaining how all that works and what the Turing test is, and how the Turing test has sort of, in a way, misled people into focusing on this idea of fooling interrogators and so on, whereas the Winograd Schema challenge that we've been talking about is a little bit more pushing on this idea of the importance of background common sense knowledge and how that gets used. So that's the book in a nutshell.
Excellent. Yeah. I'm sure many listeners will pick it up, and I'm eager to hear some feedback from those that do. There's one detail that I kind of skipped over in the questioning that I wanted to revisit real quickly, and kind of comparing the Turing test to the Winograd challenges.
Yeah.
The Turing test, it is empirical in that we ask judges to pick something.
Right.
But it's a little bit fuzzy in that, different judges are going to rate different ways, of course. You could run the same test multiple times and get different results.
Right.
When it comes to the Winograd challenge, it seems that we have a more empirical test. Would you agree? And if so, in what ways?
Once you've got the questions laid out and you've sort of convinced yourself that the questions are appropriate for the kinds of subjects you're asking, as I say, it's possible to pose questions that are just too complicated for kids to answer. It's possible to pose questions that are too Englishy for people who are just learning English to answer. But once you get that sorted out, the idea is that you would have these questions in a library or something that you could select one word or the other to put in the questions, which will determine what the answer is, and present these to a program without any judges involved at all. In other words, you pick one word or the other. In the case of the trophy in the suitcase, you pick out whether you're going to use small or big. You flip a coin, you decide which one it is. Okay, that's the question now I'm going to ask. You get the answer back from the program. You check to see whether it's correct or not. So you can do it completely without any judges involved in the actual testing of subjects. So I think that is a possibility, but it does simplify things a little bit. In particular, you've got to, first of all, make sure that the questions that you have are appropriate appropriate for the subjects that you're posing to. In other words, I don't think it's fair to apply this test to children if the questions are too complicated, or to people who can barely speak English, and so on and so forth. So you've got to settle all of that. But once you've got your community sorted out, in other words, you can predict that all your subjects will be comfortable with the questions. They won't sort of say, "What are you talking about, styrofoam? I've never heard of styrofoam before in my life." Once you've got that sorted out, then you can administer the test in a very kind of objective way. You don't need judges to gauge how reasonable the answers are. The answers are, there's only two choices and only one of them is right. And so you can have a program that marks your test, in other words, and decides how well you're doing. One thing I had suggested in a paper is that it might be a good idea to, before you administer such a test, to first of all make a list of all the words that are going to appear in the test and present those to your subjects, both people and to machines. In other words, warn people in advance all the words that are going to appear. This test is going to mention the word trophy, it's going to mention the word suitcase, it's going to mention small, it's going to mention big, it's going to mention this and that and the other thing, and you give them a list. Before you even start, they're already, there won't be any surprises in terms of any of the words that appear. And the interesting thing about these Winograd sentences is that even if you know what all these words are ahead of time and you're very comfortable with all of them, it's still going to be the case that I believe it'll be hard for computers to do it without understanding what this sentence is saying. In other words, it's not just a matter of knowing what the words mean, it's how they are being used that determines the answer to the question. And so knowing the words is not giving away too much. And so I think that that's one way of making the test a little bit more objective.
Wow, that's an interesting twist because, at first, to my ears, it sounded like a tremendous advantage because one could go and hard code a bunch of things in about that limited vocabulary. But as you point out, it's really about the semantic relationships.
That's right. So even if you know both what small and big mean, and you know what a trophy is, and you know what a suitcase is, you've got to do some extra work to figure out, if I say that the trophy wouldn't fit in the suitcase because it was too small, to figure out that it's the suitcase that's small, not the trophy, right? It's not part of the meaning of small, it's not part of the meaning of suitcase or the meaning of trophy, and it's not part of the meaning of fit either. It's putting all these things together and thinking it through that makes the difference, I believe.
Absolutely. Well, Hector, thank you so much for coming on the show and sharing your expertise and background in this. Really interesting discussion.
Well, my pleasure. Thank you.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.